if you were an Ethernet card, you'd know that that sequence meant you need to pay attention. I'm so sorry. In our last video, we talked about making a sequence of decimal integers using a block of memory cells, D flip-flops. Now, what we're going to talk about now is slightly different. We're going to switch our attention to making sequences of binary numbers. And that shift is going to change our design process significantly, because now, instead of all of the flip-flops containing the value that we're going to be incrementing or changing or jumping from integer to integer, now what we're looking at is just that last flip-flop. And that last flip-flop is going to be part of a shift register. If you recall from our discussion about linear feedback shift registers, what we had was a sequence of these D flip-flops where the value was shifted from one D flip-flop to the next. And in the terms of this external one, we had a linear function that generated the next element to go into the shift register. We're going to use this same design structure in order to create a sequence of binary values. Now, these binary values could do anything from generating signals that are a division of the clock frequency that we're driving the system with. We could get error codes. We could get test sequences. We could get pseudo random number generators, any number of things. So let's go ahead and start by just showing you an example. The circuit we're going to start with is a divide by 5 circuit. Now, if you go through our computer organization videos, you should see this divide by 2 circuit, where what we did was we took the inverse of what was stored inside the box, made that go into D, and if we had some sort of a clock frequency F that went into this circuit, then what was coming out of Q was a frequency divided by 2. So if you had, for example, a falling edge D flip-flop there, then what happened was every time we had a falling edge on the frequency input clock, then our what was stored inside the box flipped, inverted. And so what we did was we divided the frequency in half. Now you could cascade these. You could have a divide by 4, a divide by 8, a divide by 16, but you couldn't get a divide by 5. If you want to do a divide by 5, we're actually going to have to use a sequence generator, one that generates a binary sequence. And so it might look something like this. If I had my frequency that came in, and let's say again that we've got a falling edge. If I want to divide that frequency by 5, it might look something like this. So falling edge, and maybe we have 1, 2, 3 falling edges, and then 1, 2, something like that. And granted, this is not a 50% duty cycle, but it's good enough whenever we're looking at just simply getting a rhythm going of a 1/5 of an original frequency. So what you really have here is 1, 1, 1, 0, 0. That is our sequence. So what we want to do is drive a sequence generator so that we get this pattern 1, 1, 1, 0, 0. We're going to go through a design process similar to what we discussed when we talked about the linear feedback shift registers, where we were talking about shifting values through, and the last flip-flop is going to output that particular value. Now remember, the shift registers meant that the contents of those D flip-flops moved one position to the right with each clock pulse. But we also had a discussion about the number of flip-flops that were needed based on the number of states that we needed to represent. And in this case, we have 5 states that we're going to need to represent. The first one, second one, third one, first 0, second 0. So there's 5 states. Now remember, we need to have enough flip-flops to represent all 5 of those states. And so that was something like 2 to the n, where n is the number of flip-flops, minus 1. We take out the all zeros case. We'll talk about that again in a later video. So 2 to the n minus 1 has to be greater than or equal to k, the number of states we've got. And in this case, we've got 5 states. What n satisfies that? Well, the n that satisfies that, 2 is not enough. 2 is 4 minus 1 is 3. That's much less than 5. So 2 to the 3 is going to give us 8 minus 1. That's 7. 7 is greater than or equal to 5. So it looks like we are going to need at least 3 flip-flops. In a later video, we might talk about why n may need to be even greater than the smallest value that will satisfy this expression. So we're going to start out with 3. And so I've got 3 of these D flip-flops. So we've got D, Q, D, Q, D, Q. We've got our clocks, right? And all of our clocks are connected together, being driven by a common clock. And what I'm going to do is I'm going to label these just to keep things straight so that we know what signals we're looking at. We need that A, B, and C. All right, so I'm going to start designing this based on those 3 values in the flip-flops. Let's do a truth table. So we've got A, B, C. Now, what's going to happen is we're going to cycle through. We're going to just have 1, 1, 1, 0, 0. And that's the sequence we're looking for. And as that gets shifted across, we're going to see that the value that is the last is going to become the first in the next stage, and then we have 1, 1, 1, 0. So I don't know if this is going to make sense to you, but basically what we're looking at is this value is going to get shifted in through these different stages of these D flip-flops. And so the next one will take this bottom state here, loop it back up to the top, and then all of these get shifted down by 1. All right. And so what's going to happen is at time 0, we'll have 1, 1, 0, 0 in those 3 flip-flops. We get a clock pulse, we'll get the next one, 1, 1, 0. Get a clock pulse, we'll get 1, 1, 1. Get a clock pulse, we'll get 0, 1, 1. Get a clock pulse, we'll get 0, 0, 1. Now, the important thing to note is that this particular sequence really doesn't have a beginning and an end. All you're looking for is to get this sequence going over and over again so that we get this divide by clock application. Now, what is needed at the input of A? In other words, at this input of A, when we get a clock pulse, that's what's going to be stored in A. So at time, we'll just say this at this first time 0, right? We'll have A in, and that's going to be this position right here, AM. Then what this is going to look like is 1 clock pulse earlier than what's showing in A. So this will actually be, this 1 right here is going to drive that 1, which is then going to get passed to the B at the next clock cycle, which is then going to get passed to C in the next clock cycle. The next state, we're going to say that 1 is the one that's going to get passed to A on the next clock cycle, which is going to get passed to B on the next clock cycle, which is going to get passed to C on the next clock cycle. Then we have 2 zeros and this 1. And so really what we're looking at is these values of A in are what need to be present at the input of A before the clock cycle happens so that they can get moved in on the next shift. And then these values of A are needed to be the input to B so that on the next clock cycle they get shifted into B. And so we get this connection that A drives B and that B drives C. And remember that we're going to get this coming back along with other inputs from A and B to drive what's going in to A. All right? And so there's our general circuit. What we're looking for is the function that goes in between here to drive AM. And so really what this is a truth table, except what I'm going to try, the signal that I'm trying to find the expression for is A in, and usually you have that on the right side of your truth table. So I'm actually going to move this over here so that it makes more sense for us logically, in our development. So I'm just simply going to copy this column over here at 1, 1, 0, 0, 1. And in fact, I can just go ahead and erase this column because I just put it on the left side so that you could see it was driving A. So can we come up with a function that describes this truth table? Now, before we do, what we have to do is make sure that there is no point at which we duplicate the rows of the values that are going to be in A, B, and C. Because if we duplicate, for example, if as I was going through this table, 1, 0, 0 occurred again before our full period, then actually what's going to happen is that's going to reset and make our period smaller. So if 1, 0, 0, for example, happened again here, we'd never see these values. It would just loop back around to this beginning here. We don't want that. And so I look through here and I've got 1, 0, 0. That doesn't occur anywhere else. 1, 1, 0. That doesn't occur anywhere else. All ones doesn't occur anywhere else. 0, 1, 1 doesn't occur anywhere else. And 0, 0, 1 doesn't occur anywhere else. So it looks like if we can implement this truth table in circuitry up here, we'll have our divide by 5 circuit. So let's go ahead and make a Karnow map out of this guy. Okay, and remember our Karnow map discussion earlier in our computer organization theory. We numbered the rows using gray code 0, 0, 0, 1, 1, 1, 1, 0, and then the columns were 0 and 1. So now one row at a time, I'm going to transfer this truth table over into this Karnow map. So 1, 0, 0 has a 1 in it. So 1, 0, 0 has a 1 in it. 1, 1, 0 has a 1 in it, so 1, 1, 0 has a 1 in it. 1, 1, 1, 1, 1, 1 has a 0 in it. 0, 1, 1, 0, 1, 1, that's this cell right here, has a 0 in it. And then 0, 0, 1, 0, 0, 1, this cell right here has a 1 in it. Now, what about the unfilled cells? Well, the unfilled cells are don't cares. We put X's in there, which should give us, well, we should be able to figure out, hopefully, what our best case scenario is for grouping these elements so that we can have a most simplified sum of products expression. And so we have a rectangle here. There's one rectangle. And that one's pretty simple. That one just simply says, as long as C is a 0, we want to output a 1. Remember, these wild cards can be 1s or 0s. Right now, we're going to set those guys up as 1s so we can have a very simplified C bar as part of our sum of products expression. Now, that still leaves this one uncovered. The biggest rectangle I can make out of that guy, I can't use the 0 below it, but I can pair these two together. And then I can also loop around to the bottom row of our Karnow map to include those two. So I've got that rectangle right there. And that rectangle says that as long as B is a 0, I want to output a 1. So that's OR B bar. Now, what I've done, just as a real quick recap, is I'm trying to figure out what AN needs to be in order to drive this set of shift registers to output this sequence. That's all this expression is what AN needs to be. Turns out it's pretty easy. It actually becomes just the OR of not C and not B. All right? That got a little messy there, didn't it? So, and in fact, these flip-flops, they tend to also have Q bar, the inverted contents of each one of these flip-flops, and I could have just taken Q bar and connected those two instead of using the inverters here. And this guy inputs to our circuit. There you go. So as every time I get a clock pulse, those clock pulses are going to shift these values through so that this output right here, or in fact any one of these signals right here, are going to be this frequency of the clock signal divided by 5 in order to get this sequence right there. Now remember, we had talked about 0, 0, 0 not being valid contents for this shift register. So we would really like to make it so that that never happens. One way of doing that is by simply saying, okay, if all three of them are 0, then we want to make sure that we output a 1 there. Well, how do you do that? Well, remember, we've got the thing called a decoder, which says that if there's a certain condition at the inputs, it'll be a logic 1. And so I'm going to put inverters at the input here and just simply say if C is a 0 and B is a 0 and A is a 0, then what we want to do is put a 1 into A in. How do we do that? Well, we can say that if this is driving a 1, or we can force a 1 by saying if all three of them are 0, we are going to output a 1. We can put that into an OR gate, and that will give us a way to protect ourselves from ever accidentally getting into the 0, 0, 0 state. Now, this particular circuit, if we did get into the 0, 0 state, these two guys would actually both contain 0, which means their inverses would contain 1s, which means that guy's going to output a 1 anyway. So this protection circuit is not necessary with this circuit, but I just wanted to let you know, in order to avoid going into the 0, 0, 0 condition or any of these other conditions, I can just simply put a decoder here and OR its output into A in to make sure that we can recover or get out of that bad situation. Let's do another example. Let's talk about error codes. Sometimes if you don't have a display or the display is not up and running yet, you need to give the user some indication as to, where to start whenever it comes to investigating why the system's not up and running. So what I want to do is come up with a little bit of hardware that does an error code where you've got a short blink, followed by a pause, followed by a long blink, followed by a pause, followed by a short blink, followed by a long delay or a long pause. Now, why would we want to do this in hardware? Well, there are a couple of reasons why we would. First of all, we're talking about low power applications here. Low power applications, we don't want to have a processor chewing up a lot of power just to make blinking, right? It may be that you have a sensor, something that's not very intelligent, doesn't have a processor associated with it, a simple sensor. You need to be able to indicate life to the outside world, showing that something's going on. So what we're going to do is we're going to create this sequence. We're going to go 1, 0, 1, 1, 0, 1, 0, 0. All right. So there is our sequence. And in fact, if you look at that, there's 8 bits. And remember, we need to have our number of flip-flops. We need to have 2 to the n minus 1 is greater than or equal to our number of states, which in this case is 8. And this gives us an n equal to 4. Now remember, it's possible that n will go higher if, whenever we do our truth table, we find out that there are duplicate rows that would make it so that we would loop back to the beginning of the sequence before we would intend to. So we're going to do the same thing we did last time, where I'm going to simply give, and we're going to have 4 flip-flops this time. We're going to have A, B, C, and D. And this is the sequence we're looking at. So the sequence that's going to run through this, remember these are shift registers. So this sequence is going to run through these guys. And so each time we get a clock pulse, the sequence is going to go to the next cycle for each one of these latches. So it's going to start out, we're just going to, and remember the sequence can play over and over again. So we're going to do 1, 0, 1, 1, 0, 1, 0, 0. There is the sequence. If it's shifted so that the B gets the value of A at the next clock cycle, we'll take this 0 from the bottom, put it up here, and then each one of these gets shifted down by 1 cycle. Remember, each row here represents a single tick of the clock. So we've got 1, 0, 1, 1, 0, 1, 0. And then the same thing's going to happen with C. We're going to take the one that's at the bottom, put it up at the top, and then each one of these is going to be shifted by 1 clock cycle down, right? And then D gets a 1. And then we've got 0, 0, 1, 0, 1, 1, 0. All right. And so that's what's going to be shifting through these registers. And if you look at D, or if you look at any of them, you're going to get this sequence repeating over and over again with a period of 8. Now, what needs to go into A? Remember, A in, the input of A is going to be what's going to be in the next clock cycle to get A to do these things. So remember, the 0 is what's going to be in AN 1 cycle before A needs that 0. And so you're just going to get this all shifted up by 1, and then the bottom one is going to loop around, or the top one is going to loop around from the bottom on our input. So here is our input to get A to do this. Now remember, just to make things conventional for our truth table, I'm going to make a copy of A in over here. We'll do 0, 1, 1, 0, 1, 0, 0, 1. I can get rid of this column here because it's duplicated. And now we've got a partial truth table here, which we can use a Karnow map in order to figure out what the best sum of products expression will be. Now this time we have got a 4-row by 4-column Karnow map because we've got 4 inputs, right? 2 inputs are going to identify the rows. So we have A and B identifying the different values that you'll see on the rows, C and D identifying the column values, all right? And now each one of these cells represents a different possible combination of A, B, and C, and D. Now notice we don't have all of A, B, and C, and D represented here. For example, the all zeros case and the 0, 0, 0, 1 case, those are not appearing in this truth table, but they are represented in this Karnow map. We'll just put don't cares there because we don't care for that particular situation. Remember, we could also add hardware in there that makes it so if we do get into one of those conditions, we can get back out in a hurry if we want to. So 1001, that's 1001, this cell right here. So when we have this case right here, we need AN to be a 0. Remember, this Karnow map represents the expression that we want AN to be. Next row, 0, 1, 0, 0. So we have 0, 1, 0, 0. This cell right here, AN needs to be a 1. And then we have the third row, 1, 0, 1, 0. So we have 1, 0, 1, 0. This cell right here, 1, 0, 1, 0. That's a 1. The next row, 1, 1, 0, 1. 1, 1, 0, 1. This cell right here gets a 0 for AN. Then 0, 1, 1, 0. 0, 1, 1, 0. This cell right here gets a 1. Then 1, 0, 1, 1. 1, 0, 1, 1. This cell right here gets a 0. Then we've got 0, 1, 0, 1. 0, 1, 0, 1. This cell right here gets a 0. And then the bottom row right here, 0, 0, 1, 0, 0, 0, 1, 0. This guy gets a 1. All right. Everything else is a don't care. All the rest of these cells are don't cares. So they can be wildcards. They can be used as a 0 or a 1. Either way. Just to make the simplest circuit, we'll go ahead and pick. Now, it looks like we've got a real easy rectangle here. This rectangle right here will cover all of our 1s, not cover any 0s, and use wildcards as needed. Well, it turns out in order to get a system that looks like this, you're looking at as long A and B have no effect. So A and B don't play any part. A and B can be whatever they want to be. But C and D, it looks like as long as D is a 0, AN is a 1. So it looks like our expression is just AN is equal to D bar. As long as D is a 1, as long as D is a 0, AN is a 1. So we draw our circuit. We're going to have 4 of these bits in our shift register. So D to Q, D to Q, D to Q, D to Q. And so this is going to be A, B, C, and D. All right. They're all driven by the same clock. So these little triangles here represent the input for the clock. All right. So there's our clock. And what we've got is, at this point right here, this is our A in. So what drives A in? Well, what drives A in is just the inverse of D. Now remember, these flip-flops could have Q bar as an external output. I'm not going to use that. I'm just simply going to do the old-fashioned way of putting an inverter there. All right, and that is enough. That circuit right there, wow, pretty simple. that circuit right there, if you were to run this with a clock, what it would do is repeat that sequence over and over and over again. Well, as long as you have power. In our next video, we will be talking about how these binary sequence generators made from these linear feedback shift registers are used to create pseudo-random number sequences for applications in our computing systems.